This conference will now be recorded.
Good afternoon.
Good afternoon, ma'am.
Good afternoon, ma'am. Good afternoon.
We'll be starting with the next small topic in the chapter, drug stability, where you'll be understanding kinetics of stability and stability testing. That is a general aspect of this topic. You'll find it in the Martin textbook also, or you can also refer the Latchman textbook when you get the option to refer. So many I've been telling there are topics like it is based on your basics, so we don't get much time to discuss in detail because we need to run with the syllabus. So this drug stability also you would have learned in your UG syllabus in the physical pharmaceutics, as I remember. So quickly we'll be going through the stability aspect of the drug, because last class we learned about, that is last topic, whatever we learned was on the drug excipient interaction, and that interaction, how to measure that interaction we have understood now, the equipment or the analytical technique used for measuring the interaction. So ultimately why it bothers us, the interactions are so important, because why it is need to be given so much of importance for the drug excipient interaction, because it is stability aspect. Ultimately the dosage form should be stable and it should be having the required shelf life, so that when it reaches the consumer, that it should have been the normal stability status. So adding to that only, we'll be learning the another topic, drug stability aspect. So it's one of the requirement here which FDA made it mandatory and which comes as a part of good manufacturing practice. So I missed out one of the other thing is there are different guidelines you get it, and one of the guidelines is ICH guidelines also for the stability studies. So those are the regulatory aspects, the guidelines given in even in the WHO guidelines you get, okay, FDA guidelines or the ICH guidelines. So guidelines are the like rules and regulations which need to be followed to study the stability aspect of the drug. So that's part, and it becomes mandatory for also us also to understand what exactly this stability study means, and that stability depends on the kinetics. So before that, let me give you a brief view on the degradation process. See, that's what the stability is, nothing but what something is going to be changed with respect to the drug molecule or with respect to the dosage form, which is not acceptable for us, or which might disturb the therapeutic action ultimately. So this degradation can happen either chemically or physically. So chemically, the obvious change in the chemical aspect will happen, and the physical it may be with respect to the visual changes or even with respect to the crystalline properties of the drug. It's also physical property. Crystal, when we say crystalline, change in the crystalline property of the drug, it will not change in the chemical composition or the chemical structure. So because amorphous form, crystal polymorphism, if you remember, there you would have learned change in the crystalline structure without disturbing its chemical structure. So all that will come under physical degradation. For means the drug as such, I'm not talking about any excipients here now. I'm just talking about the drug. So the drug as such can undergo degradation either by the chemical route or by the physical route. Okay, so when just in a quick glance, we are going to understand the each process quickly. I'm telling it's a repetition. It's a revision I can call, not repetition. It's a revision for you to understand what are the reasons for the drug to undergo degradation. And these are the examples by which the drug can get degraded by chemical routes. Solvolysis, oxidation, photolysis, dehydration, racemization, incompatibility, and also any other changes which happen due to the hydration and the decarboxylation. We can keep on classifying like this, depending, because ultimately degradation is a chemical. Most of the time degradation is a chemical process. Okay, so we can keep on adding varieties of routes of degradation. The simple one I've just highlighted here, it can be like one-step degradation or the two-step degradation. You can understand it can degradation can happen in the multiple steps also. So let's look into the few of them. Solvolysis process, it's nothing but the decomposition which is happening because of the reaction between the solvent, that is a water molecule, especially water molecules which are present. And that's something simple. Other way of expressing solvolysis is hydrolysis. So, or it can also happen with some of the other co-solvents which we are adding along with the co-solvents present along with the drug molecule during the preparation process. So the solvolysis doesn't or not only talks about the hydrolysis, it also emphasizes on the other solvent, the interaction happening because of the presence of the solvent which is present around the drug molecule. So what happens generally is the solvents are nucleophiles in nature and have the tendency to attract the electro-opposite centers which is present in the drug molecule. This simple mechanism I'm trying to explain. So nucleophiles which are present in the solvent can interact with the positive charge of the drug molecule, electropositive charge present in the drug molecule, which results in the solvolysis process. So some of the examples which undergo this degradation is carbonyl compounds, or let us look into the example of the drug itself: aspirin, spironolactone, penicillin. All these are the drugs which are sensitive for this solvolysis degradation process. And this degradation, when I talk, this also depends on the pH. So anything happens, any change happens to the APA molecule, it's nothing but it's a degradation, and that change can happen because of many reasons around, because of the environmental factor. So it's not a like simple topic that we can discuss in 1 hour. So it's just examples I'm giving you. So they are all dependent on the many factors like temperature, pH around the drug molecule, okay, humidity also, even the pressure also sometimes plays its role in undergoing the degradation process. You can imagine the complexity. So it can happen because of any reason. So ultimately, we need to understand the degradation so that what we can do, we can come out with a suitable processing method also. We can come out with a suitable packaging method also, or we can decide about the storage conditions also. Ultimately, I want the drug, or we want our drug to be stable. How we do it, that depends on how it's getting degraded. So we can avoid this degradation when we have the knowledge about the degradation process. So we can minimize that when you know the fact, or when you know the reasons for the same. So like this was a solvolysis example. Same with the oxidation reaction, simple term, which you've been learning about this mainly because of the presence of the atmospheric oxygen. So okay, so this can happen. It is mediated to either to the atmospheric oxygen under ambient conditions. This ambient condition is a suitable condition called as auto-oxidation process can happen. It's nothing but the free radical reaction. So oxygen itself can act as, so oxygen may not directly interact. It generates the free radicals, means it get converted into high energy state, and then it becomes very reactive. So it's like auto-oxidation process, it is called as. So the functional group generally which is susceptible to this kind of reaction is phenol, ethers, amine, aldehyde, thiols. So okay, these are some of the examples of the functional groups which are present in the drug molecule which may be sensitive for the auto-oxidation reactions. So these reactions are mainly catalyzed by acids and bases, and they trace even the amount of the impurities like metal ions or hydroperoxide. So like this means I'm giving you an idea the how the degradation can happen. It's not only the presence of oxygen, it is converted into highly reactive form, but also this can be even triggered in the presence of the some of the other impurities also. It's fine. So now this is just an example oxidation process. Parahydroxybenzoate, which is formulated in a suspension containing PAG, turns to yellow under ambient condition if not protected by oxygen. So like this kind of unacceptable changes can happen in the product. So we need to take care of, like maybe like we need to avoid the PEG, or maybe that you need to remove the oxygen completely in the container so that we can minimize this kind of unwanted reactions. So here also I suggest you to remember some of the example while writing your answers. So that's about the oxidation. We started with what? We are talking about the degradation process of the drug molecule. Why we are talking about degradation process? Because we are trying to understand the stability aspect of the drug. And this degradation can be either chemical or physical. In the chemical, there are varieties, and some of the examples we are trying to learn is solvolysis. We understood mainly because of the presence of the solvent molecules around the drug molecule. and they are highly nucleophilic in nature, which attracts the electropositive center of the drug molecule. The next one is the oxygen, that is oxidation reaction, and of course the oxygen is responsible for that. And this can also be triggered by the other factors, which can be impurities which would have been added during the processing also, because metal ions and all, what you can expect, from where you can expect, we are not deliberately adding from our side. Okay, maybe that it may be during the processing, the wear and tear of the equipment would have happened and it got added. So like this, there may be many reasons for that impurities, which also triggers the oxidation process. Next one is the photolysis. So term itself tells, so whenever you look at the word, read the word solvolysis, oxidation. The next one is photolysis. You can easily identify the which kind of reaction they have. So photolysis, definitely they are because of the presence of light. And this degradation is mainly can happen because of the radiation which is absorbed by the molecule to cause a photolytic reaction. Means if the drug chemical structure has the capacity to absorb this radiation, then only you can expect this kind of photolytic reaction to happen. And this reaction can happen mainly because of the pi electrons absorbed. These molecules with the pi electrons. So these molecules, what I'm talking about, the drug, whatever the drug is sensitive for photolysis, we generally will have a pi electrons, and these pi electrons have capacity to absorb the UV radiations, or near the, or not directly the UV radiation, but also maybe the radiation near to the UV range. So below 280 nanometer, so degraded by the sunlight, okay, and above 400 nanometer degraded both in the sun and the artificial light. So these are the nanometer range actually which causes the degradation of the drug molecule. So below 280 nanometer, it is degraded by the sunlight. Means the sunlight can also be directly, the sunlight may be the reason for the degradation, where the below 280 nanometer usually take part in the photolysis, and above 400 nanometer, when you talk about, even it can degrade in the presence, which has capacity to absorb 400 nanometer, it can degrade both in the sunlight as well as the artificial light. So it depends on the capacity of the chemical structure of the drug molecule, which can absorb this range of nanometer. So accordingly, you can expect the type of degradation happening. So this is very challenging thing for us, especially those drugs which absorb 400 nanometer. Means artificial light can also influence. So you should be very careful in packaging those kind of drug molecules, and the packaging should avoid the entry of this rays, so that we can minimize the degradations. So it is, though photolysis we say depends on the chemical structure, it is also associated with the oxidation. So that's the reason we call it as photooxidation process. Means this kind of photolysis reaction can be triggered in the presence of oxygen, and oxidation will also be the one of the pathway by which the drug is getting degraded. So it's called as photooxidation process. So phenothiazine is one of the example, and same here, sodium nitroprusside is also one of the example, which is in aqueous solution, can result in the photolysis. So drugs will absorb greater frequency light cause phototoxicity by generating singlet oxygen. So this is the mechanism. What happens when it absorbs the light, especially at the higher nanometer range? It generates the singlet oxygen. It's one of the form of the oxygen. So singlet oxygen is a form of the oxygen which is highly reactive in nature. The oxygen as such can involve in the oxidation, but oxygen in the form of the singlet oxygen is highly reactive with respect to the reaction capacity. So it also, and that results in the photooxidation process. And this is a mechanism. So excited oxygen with unpaired electron is nothing but called as the singlet oxygen. So this is about the photolysis process. So dehydration. So you understand dehydration very well. So elimination of the water. No doubting that dehydration. Hydration, dehydration, opposite to each other. So examples of the drug is, please note down these examples, whatever I'm telling, or it's better to remember this example, prostaglandin and the tetracycline. Try to remember one which is common examples for you to remember easily. Okay, so like tetracycline is easy for me to remember, so I'll try to remember tetracycline. Like penicillin in the previous case, so I might try to remember the penicillin like this. So this dehydration can result in either the chemical dehydration or the physical dehydration process. So in case of chemical dehydration, chemically there is an interaction happening. So removal of water results in formation of the double bond that can participate in electronic resonance with neighboring functional group. So if you are a little strong in the chemistry, maybe it will be easy for you to quickly grasp it. Okay. So I'm not a person, a chemistry person, so I really struggle to sometimes understand what is this electronic resonance, but I'm not bothered. What I am actually understanding is, if you ask me how I actually understand it, it's a chemical interaction. So when I say chemical interaction, there should be something happening, chemically changes should happen, and that change is happening because of the formation of the double bond. And what happens when the double bond is formed? That can which results in the electronic resonance, and that happens with the neighboring functional group. And neighboring functional group is what? The functional group present in the drug molecule. So this is how you are supposed to remember, though you are strong in chemistry or not. If you're strong in chemistry, as I said, it's left to you how you remember. Ultimately, the chemical degradation, so dehydration, sorry, it results in the change in the chemical structure, mainly because of the formation of the double bond. So same way in the physical changes when we talk, this is what I was telling you, polymorphism, crystalline structural changes, where though the crystalline structure is changed, is a physical activity, physical change happening. So what happens here? Its physical properties might get disturbed. That's what we learn in the polymorphism. So they are the crystals, they are the different crystals with the change in the crystalline property, but having the same chemical structure, but vary in the physical properties. Like melting point will vary, solubility will vary. So all this is nothing but called as a physical dehydration process. So racemization also. So if, as I was telling you, depending on the type of chemical changes happening, you can keep on giving the different names. So these are some examples taken from the textbooks. So just for your answer points, I'm telling you. So this racemization is another one of the chemical process. So enantiomers are formed after racemization procedure, which can affect the ADME process. I'm not expecting you to understand what is this exactly. Racemization is, I remember in the B Pharm we used to study in detail what is racemization. But for today's purpose, I just want to know, I try to remember that racemization can happen, is one of the chemical changes happening to the drug molecule and which can affect the ADME process. And some examples of the drug molecules are this one: pilocarpine, epinephrine, ergotamine, tetracycline. All this can undergo racemization, and it is catalyzed by acid or base. This is the only thing I try to remember. I'm not going to explain, or I don't expect you again to remember the detailed, that concept. Not required for our purpose. So that was about the racemization. When I say about the incompatibility, actually it's a very general term we are using here. Incompatibility, which happens between the two drugs when you try to prepare the combined drug dosage form. So gentamicin and kanamycin, which forms a complex, and that disturbs the in vitro and in vivo performance. Means it can happen during the processing also, or even it can happen inside the body also. So it affects its performance, its action, whatever you call it. So, okay. So that's about the incompatibility which happens due to two drugs presence in the same dosage form. And it can also happen with other ingredients, which now we are very much confident, I know, because you already completed this topic. Other ingredients, when I talk, it's a drug excipient interaction. So compatibility, chemical instability can also happen because of the interaction between the two drug molecules, or the interaction happening between the drug and the excipients. So coming to the decarboxylation, so it's a decarboxylation is removing the carboxylic acid group. So para-amino-salicylic acid gets decomposes with evolution of carbon dioxide to form monoaminophenol at 40 degrees centigrade. So these are some of the examples. Okay. So if you can remember, you remember, otherwise forget it. So like this, chemical degradations can be categorized into varieties. So we got to know now that a drug can get degraded because of many reasons. So coming to the physical, when we got some idea about the chemical, let us also look into the physical aspect, physical degradation process. So polymorphism, pseudopolymorphism, that's where the major physical degradation comes into picture. Okay, they are the crystals prepared by using different solvents. So polymorphism, This information I'm telling you, I've been telling you before also. I told you they are the different forms of the crystals of the same drug, which have the different physical properties but same chemical structure. So they exhibit the different physical properties. That's what I was saying. Melting point, solubility, even the color, they might be different. So this kind of change can happen. See, for example, alpha, beta, gamma polymorphs may be there. Among that, beta may be showing the good activity, that is solubility. So I'll be selecting beta and I'll take forward it for the formulation. So during the formulation, I should make sure that nowhere it should lose its beta form. It should not either change into alpha form or it should not change into the gamma form. This is an example I'm talking. So means the processing factors, the environmental factors like temperature, any of this can affect that polymorphism property. Humidity, comminution is nothing but that is size reduction process, granulation, milling, compress. What I was saying. Any of these processing factors or the environmental factors should not affect the original polymorph of the drug. Fine. By chance, if it's an amorphous drug, you should take care that it should not be getting crystallized. It should not be converted into crystalline nature. So because amorphous form has a greater solubility compared to the crystals, and it is more hygroscopic in than the crystalline counterpart. So problem with amorphous is what? Of course, it has a good solubility, no doubt. So but if I don't take care of its storage condition, what happens is they're hygroscopic in the sense they can absorb the moisture. So if they absorb the moisture, presence of moisture can result in the hydrolysis process if it is sensitive to the hydrolysis process. Or not only that, the moisture can change the amorphous form to crystalline. There is a chance that anything can happen to the property of the amorphous drug. So like this, the knowledge of the API will help us to decide with many things. So pseudopolymorphism, just an additional information. They are nothing but the polymorphs which are of the same, what do you say, where the crystals have been produced by selecting the different solvent, and during the crystallization process, this solvent get entrapped inside the crystals. Okay, they will have the same crystal structure. Pseudopolymorphism means they have the same crystal structure, but the solvent whichever we would have used for crystallization process, that gets entrapped inside the crystal. If it is the aqueous, like water is used as solvent, the water get entraps, then you call it as an hydrate. If you're using the organic solvent, then what happens? That organic solvent get entraps inside the crystal, then you call it as solvates. So those are called as pseudopolymorphism. But in case of polymorphism, whatever you have, I just told before, see that is polymorphism is different. Pseudopolymorphism is what? During the preparation of the crystal, the solvent is getting entrapped. So there is no change in the crystal structure. But in case of polymorphism, the crystal structure is getting changed. So that affects the physical property. Change in the physical property happens because of the change in the different form of the polymorphs. But in case of pseudopolymorphism, there is no change in the polymer, that is crystal structure, but the solvent entrapped between inside that crystal structure will be either organic solvent or the aqueous solvent. So if it is aqueous, it is a water, you call it as a solvates, or sorry, hydrates. If it is organic, you call it as a solvent. So that's when the anhydride, monohydrate, dihydrate, the trihydrate, tetrahydrate, all the terms will be added when you designate the particular crystal. So that's about the pseudopolymorphism, which mainly dependent on the environment, especially the temperature and the kind of solvent present around the drug molecule. So vaporization is the next one. Some drug, you are going to lose it under particular temperature and the pressure. That means the original quantity of the drug, whatever you would have used, that get vaporized. So because of its property. So then that is mainly affected by the temperature around it or the pressure we are under which we are processing that particular drug. So exhibits greater vapor pressure at room temperature and results in the drug loss. Greater vapor pressure in the sense it gets vaporized. So the concept of vapor pressure, all that if you have thorough understanding, it becomes easy to understand this concept, whatever I'm telling you. So the example is nitroglycerin is one of the best example. So the drug loss, that's what ultimately that degradation in the form of loss of the drug is. So chemically it may not be affecting anything, or physically no change is happening, but we are losing that drug. And this drug amount initially whatever we would have used, by the end of the process you may not get the same amount. You would have lost because of the vaporization. So knowing this reality, what they do is they try to minimize it by adding some of the components like PEG, PEP and MCC, and we can minimize that vapor pressure. So greater the vapor pressure, greater the vaporization. This much I can tell you right now. So that's how the degradation can also be related to loss of the drug itself, can also be a degradation process. So aging aging means it's one of the reason for the drug to get degrade. So because of the life, it's getting age. Change happens with respect to age of the dosage form. So nice to say in this sentence, change happening with respect to age of the dosage form. So means what happens? These are the changes which might happen during the storage conditions. So this process through which change occurs in the disintegration or the dissolution characteristics. Mainly it can affect the disintegration or the dissolution characteristics because of the aging process. For example, is melting point of see, look at the original properties only is getting disturbed. So the melting point of aminophylline suppositories increased from 20 minutes to 1 hour. So when you prepared this dosage form, the melting point was like little what you call that aminophylline, where it were much what you say the suppositories. We remember this aminophylline suppositories 20 minutes to 1 hour means before it used to get melted in 20 minutes when you administer into the body in the body temperature. But due to the aging process of the dosage form, what happened? It's taking almost like a 1 hour. So you can imagine that because of that dragging or delay in the melting process, the effect also will be delayed. So then definitely the bioavailability will be affected. That affects the action. So this is something called as the issues which is happening because of the aging process of the drug. And that aging process can affect the function, that is dosage form integrity. Like one example is suppositories where its melting point time only change from 20 minutes to 1 hour. Another one that it can affect the disintegration. It may not disintegrate only the drug tablet. So no disintegration, no dissolutions. So this was the result of interaction between the drug and free fatty. So this aging factor is mainly because of the presence of the additional excipient also. So like this, these are some of the example I just gave you to get an idea. So reasons for the drug to degrade. So now coming to some of the other physical method of degradation process, adsorption and absorption. Okay, it's where chemically nothing is happening, but the process it's been disturbed. So plastic interaction, drug plastic interaction can happen during storage of the solutions in the PVC container. Okay, same thing, 50% drug loss they have absorbed when nitroglycerin was stored in the PVC container. Because of the adsorption process, the container is absorbing that drug. So even that is also loss of the drug. And this, the reason for that is, they have justified with the reason is the greater partition coefficient between the dosage form and the plastic material. Okay, so like this, the adsorption can happen, the drug loss can happen because of the type of that is storage container we are using. So even that knowledge is important for us so that we can minimize the loss of the drug. And hydration, we know that absorption of the water molecule. If the storage container is not suitable to retain the water molecule to enter inside, so that results in the hydration process, and presence of water molecule can result in the hydrolysis. Later on, chemical changes can happen. So anything can happen. These are all the physical changes where the hydration is nothing but addition of the water, adsorption is nothing but where the drug get adsorbed to the packing material. So no chemical changes happen. That's what you need to remember when you write about the physical degradation process. Don't talk about the chemical degradation here. We just talk physically what is happening. So that's about the examples. Just we got an idea what are the reasons for the drug to get affected, or the reason by which the drug get degraded or affected or can affect the stability of the drug. So I don't ask you like any doubt here. Is something like a very minimum information I've given you. It's another version again. You can talk about each drug, each degradation step differently, because every drug will degrade in a different pathways, not in the same pathways, or it may degrade or it may not degrade also. Fine. So the point now which we need to learn in detail is the reactions. So whatever the degradation we have learned, got to know about little bit, all that degradation is like it's nothing but a chemical reaction happening. Means chemical changes may not happen, but it is a kind of chemical reaction is happening. So I can always relate this, or we can always relate this to the chemical kinetics. So when we say the word chemical kinetics, that means the rate at which this is happening. That is what we are going to learn. So let us understand now here, knowing the reality, the degradation is happening. Now we know that the reasons for the degradation. What is its benefit now? The knowledge of the whatever we have identified the degradation, we understood thoroughly the what is the reason for degradation. That helps me to decide with the dosage form stability, in the sense whether the degradation is happening during the processing or happening during the, as I said, packing or during the storage. All this information will help us to decide with the conditions required, so that I can minimize the degradation, or even I not minimize, I need to avoid the degradation happening, so that ultimately the dosage form, when it reaches the customer, till its shelf life, it should be in the intact form. It should be in its original form only. So now all this how we decide that I need to change. Okay, based on the initial studies, we know where the change is happening and what are the reasons. All that is fine, but sometimes we cannot wait for the situation to come up, raise up its own. We need to actually subject it from our side only. We need to carry out some of the studies to confirm that our drug molecule can be stable enough in these conditions. And that's when we depend on a study called as stability study, and added to that is accelerated stability studies. Means we need to accelerate the condition such that we deliberately we are making the drug to undergo, we are deliberately making the drug to expose to the different condition, accelerated condition, and then cross verify whether any change is happening to that particular drug. And based on that quick trial, whatever quick study we do, we come out with the conclusion with respect to many other things like packaging, storage, all that can be decided based on this accelerated stability studies. So that's what we are going to learn in this next in continuation, means that is chemical kinetic principles. Let us understand the kinetic principles parallelly, some of the examples. So what is kinetics? Is the rate process which expresses the reaction happening. And what is the reaction here? It's a degradation happening. So degradation reactions can be understood thoroughly with the help of the chemical kinetic principles. So when we tell it's a chemical kinetic principle, so we need to understand about the kinetics. It's a rate process. How, at what rate the drug is degrading. So when we talk about the rate process, we should understand about the rate concepts also. So with this one small example, if you look at when you look at the screen here, an equation has been written. Why the equation we are writing? It's a chemical reaction. Any chemical reaction is represented in form of equations only. So when let us imagine there are two drug molecules A and B which is interacting and it's getting changed. So it is only for the understanding purpose what is kinetic reaction means. So this has been given as an example. So not every time, don't imagine drug A and the drug means always the kinetics talks about the interaction between the drug A and the drug B. No, even the degradation can happen only with the A, where the A just get decreases after particular time. So don't correlate any to the original like in the realistic situation. Let's understand in general. So if this is what the chemical equation when you write, What is the chemical reaction? We are understanding that a drug A is there, okay, and drug B which is interacting, and it is converted into two products, that is M and the N. So A and B are called as the reactants. So we are learning what is the designation they are being called with. So reactants, and N and M are called as the products. So any kinetic reaction, two things are always there. One is the reactant, another one is the products. Definitely. I mean starting material and the end. Same thing how you say the starting material and end material, here also reactants and the products. So then what is this A and B? The A and B are nothing but the number of molecules. Whatever the small letter has been designated here, A and B are also called as stoichiometric coefficient value, or the simple language for our understanding is nothing but the number of molecules. So A and B are what? A number of molecules of capital A interacts with B number of molecules of capital B. That results in the formation of M product with the M number of molecules and N product with the N number of molecules. Yes, it talks with respect to the number of molecules, interaction with respect to the number of molecules. So now what we got to know that any chemical reaction is represented by an equation with, and there will be an arrow mark which represents that that reaction is happening in the forward direction or the backward direction. It can be possible both, that whatever the arrow mark you are seeing here, it's only one direction arrow mark. There are also chance that the reaction can be the backward also. So that's with respect to the chemical reaction representation. So all that is not required. So what we should know now is, this is how the reaction is represented, and the kinetic reaction or the chemical, that is a kinetics or the degradation process is nothing but the chemical kinetic reaction. So definitely that has to be understood by writing the chemical equation. So when we write the chemical equation, this is all the important things. There will be a reactant and there will be a product, and the number of molecules taking part in the reaction also represented alphabetically. Okay, up to this fine now. Now I want to understand the change happening. What is changing? If drug A is changing, or the reactant A is getting changed to reactant M, or reactant B is getting changed to reactant N. So there is some change happening, and the change of the change, whatever is happening, is nothing but the rate of change of concentration of the reactants and the products. Whatever change is happening with respect to A or B or M or the N. See what change is happening in the A, it is decreasing because it is converted to M. What change is happening with the M, it is increasing with respect to time. Same with the B, it is decreasing with respect to time, and N increasing with respect to time, because product, no, as the B changes to N only, the N will increase. Fine. So that rate of change of the concentration is represented by the differential equation. So whatever the differential equation you are seeing here is any change happening with respect to another variable is represented by differential equations. Here we are trying to understand the change happening with respect to time. So that's the reason you get to see the equation as dCA by dt or dCB by dt. A is with respect to drug A, B is with respect to, reactant A, and the B is with respect to reactant B. And the negative sign here indicates that with respect to time, it is decreasing. That's the reason the negative sign has been indicated here. Even in this case, there is a negative sign, and in this case, there is a negative sign. But coming to the right-hand side of the equation, this is the left-hand side of the equation where the rate has been represented, and this is the right-hand side of the equation where the rate is represented. Here, the plus sign is, though I have not written, it indicates always, no sign indicates always plus. So there is a plus sign in the right side of the equation, and that plus sign is because M is increasing, N is increasing with respect to time. So that's the reason the plus sign has been designated. So understand here, this is how the chemical reaction is represented, and in any chemical reaction or a chemical kinetic reaction, there will be a reactant and there will be a product. And to understand how the reactant or a product is getting changed with respect to time, a differential equation is always used to represent that change. And the differential equation can be written like this. And in the differential equation, the negative sign indicates the decrease in the reactant, and the positive sign indicates increase in the product. Okay, hope you understood up to here. You have any doubt, clarification you want?
No, ma'am. It's clear, ma'am.
Oh, fine. So hope you are understanding the flow, whatever I'm trying to take you to the next level. So degradation happens. Degradation is nothing but the chemical changes or the physical changes happening with the drug, and that degradation can be very well understood by the kinetic process. And what kinetic process? Any degradation, generally it will be chemical interactions, chemical changes happening, and that chemical changes represented by the chemical equation and all this, whatever just now I revised. So now going ahead, later on, depending on what is that I want to measure. To say that A is converted to, for example, M, or the B is converted to N, I should able to measure A or I should able to measure M. So I should have some experimental procedure, right, to identify. Theoretical I may be saying like this, and practically I want to do this. So I should have the knowledge, what is that information, that what is that I can measure conveniently, whether I can measure A or either whether I can measure M. Depending on that, the further equation will be taken. For example, I can measure the change of the drug easily than the product, because I don't know, let us imagine, I don't know to what form the product is getting changed or the drug is getting changed. So it will be easy for me to measure the A rather than its product. So keeping that as the thing in the mind, so what I do is I write the equation. The rate of change of concentration of A at a time or any particular time is proportional to the concentration of reactants raised to the respective power. So when you read the sentence like this, it's difficult to understand, but same thing when I represent in the equation, it is easy to understand. Means the rate of change of the drug A, this one, the rate of change of the drug A with respect to time is nothing but equivalent to its initial amount and the number of molecules involved in the reaction, and its constant called rate constant. So K is called as proportionality constant. So I always expect you to remember it as a reaction rate constant than the proportion, because we are talking about, see, K is constant and there is a different constant we use in the different subjects. So here it is a reaction rate constant. So K is a constant. Fine. So the rate of change of concentration of A at time t is proportional to the concentration of the reactants, that is Ca concentration, raised to the respective power. Respective power is what? A. A indicates what? Previously we understood in the previous slide. A is the number of molecules. So respective power. This is what this statement is telling. So when you write, you can directly write this equation. It's easy for you to understand the statement. So I want to know in what rate the drug A is getting changed. The drug A is getting changed. So I write the differential equation. Okay. And then I write it equal to the rate constant into concentration A to the power of A. In this case, K is, as I said, is a reaction rate constant, and to decide which order of the reaction, it is a summation of the exponents. Exponents are what? In our case, it is A and the B, because the example what I took in the beginning, which I referred from the textbook, of course, they have taken this equation containing two reactants. So when I say two reactants, there are two different molecules. So definitely the order of reaction will be A plus B. If at all this B is not there, let me imagine there is a situation where the degradation happening without the presence of the another reactant. There is a chance, of course. So now the order will be only A, not A plus B. So like this, if the three reactants are present, it is A plus B plus C. So the order of reactants are nothing but the sum of the exponents. That's what I expect you to remember. So the order of reactants is what? It is the sum of the number of molecules involved in the reactions. In this case, the example, whatever we are learning, it is A plus B. So when I write an equation for considering both the reactants, this is how the equation comes. So more the number of reactants involved, more the complexity the equation becomes. The rate equation representation becomes more and more complex. It's not only theoretical, it becomes complex to write the equation. Even when we try to do practically, it becomes difficult for us to understand the that is reaction kinetics. Okay, so more the order of reaction, more the complexity the equations are. That much I expect you to remember till now. So now I'll be discussing tomorrow about this order of reactions. So that was just the introduction I gave you. What is the kinetic reaction means, or the and that kinetic reaction is represented by the equation, the chemical equation. Now I can call it as a kinetic equation also. And what is that? You can determine with that equation. It helps us to understand the change happening with respect to time and how you represent that change happening with respect to time, because you have written an equation in the form of differential equation. Okay. And what is the kinetic order? We understood it's the sum of the exponents, or the sum of the molecules involved. Okay. And there is a constant called as rate constant, or the proportionality constant. So tomorrow we'll be discussing. By then, please go and revise. As I was telling you, you can always Google search for the authentic article, research articles, where you can get some idea. Don't depend on the ready-made PPTs available in the Google search. So zero order, first order, and the pseudo first order. Let's revise. Let's discuss in detail tomorrow. If you have anything to ask me, you can ask. Chandana?
Yes, ma'am. Yes, ma'am.
Okay, Asha is there. I'm just calling your names. Suchitra,
Yes, ma'am.
Asha,
Yes, ma'am. Yes, ma'am.
Ashita Verma,
Yes, ma'am.
SK, Soundarya SK,
Yes, ma'am.
Prupti.
Yes, ma'am.
I think Tejaswini is not there. Prupti, ನಿಮ್ಮನೇಲಿ ಏನ್ ಫಂಕ್ಷನ್ ಜೋರಾ?
ಇಲ್ಲ ಮ್ಯಾಮ್ ಪೂಜೆ ಮಾಡ್ತಾ ಇದ್ದಾರೆ.
Today Saraswati Puja?
ಹೌದು ಮ್ಯಾಮ್.
Okay, okay. No, nice. I can hear that gante sound. So today Tejaswini is not there. Who else? Even another Soundarya is not there. See, please take care of your attendance. I told you before also. So hope you have made the notes at your side. Just go through once. Tomorrow I'll start with the other kinetics. It becomes easy. I want to run it fast little. I'm going slow, I felt. So I need to be fast, so that that will happen with your support only. I cannot just run. I want you guys to understand also parallelly. Okay. Okay, then we'll meet tomorrow.
Yes, ma'am. Thank you,
Okay,
ma'am.
ma'am.
Thank you, ma'am.